Hi Year 12, this is our final video for the topic of vectors for the International Baccalaureate course, Analysis and Approaches. In this video we're going to cover vector proof. Now we can use vectors to prove many geometric results, from theorems and rules to properties of triangles, quadrilaterals or circles, or we can prove a result in a specific shape. Now before we begin, let's look at some tips for proofs. We'll start with the properties of the scalar product, which are really useful. Particularly this first one. This says that when we take the dot product vector in itself, that's equal to the magnitude of the vector squared. We use this all the time. But these two are also important. This is showing that the distributive law works for the dot product. If we want to prove A is perpendicular to B, we show that A dot B is equal to 0. We can substitute an equivalent vector equation for an unknown vector. And finally, it's really important that you know the properties of various triangles, quadrilaterals, and circle theorems. Now, the midpoint theorem is a really useful theorem, so we're going to start off by proving it. It states that the midpoint vector OC of two vectors OA and OB is given by a half of OA plus OB. Which kind of makes sense if you look at it. This vector here is half of the addition of these two vectors. Now, this is how we're going to prove it. We're going to start off by letting OC equal OA plus AC. And so that is equal to OA plus a half of AB, because we know that this is the midpoint. We can write that as OA plus, now instead of AB, which is here, we know that that is going to be OB take away OA, and tidying all of that up, we have proved it. It's equal to a half of OA plus OB. I mentioned before that it's really important that you know the properties of the triangles and quadrilaterals. Let's start with the family of special quadrilaterals. There are 6 of them. We have a trapezium, which has one pair of parallel sides. Parallelogram, opposite sides are equal and parallel. Rhombus has 4 equal sides. Rectangle, opposite sides are equal and parallel, and all of the angles are right angles. Square, all sides are equal and 4 right angles. And kite, adjacent sides are equal. Because if you are asked to prove that a quadrilateral is a particular type, you need to know some minimum conditions in order to construct a proof. If you think about a square, for example, all you need is 4 equal sides and 1 right angle. You don't need all 4 right angles. I want you to have a think about why that might be. For a rectangle, you need opposite sides equal or parallel and 1 right angle. For a kite, you need 2 pairs of adjacent sides being equal. For a rhombus, you just need 4 equal sides. For a trapezium, you need exactly 1 pair of parallel sides. And with a parallelogram, you need opposite sides are parallel or opposite angles are equal. Here's an example. The position vectors of the points P, Q, R and S are shown. Show that PQRS is a rectangle. So we'll start with the diagram. Now if we can prove that opposite sides are equal and we have 1 right angle, then we have a rectangle. So we'll start by forming the vectors for each of these sides. Now when we form PQ and SR, we can see that they are identical, so their lengths are equal. And forming QR and PS, we can see the same thing. So opposite sides are equal. Now let's do the dot product between PQ and PS. Because it's equal to 0, we have a right angle. Therefore, since opposite sides are equal and we have 1 right angle, PQRS is a rectangle. There are also minimum conditions with diagonals, and using diagonals can be quicker. For example, if you want to prove that a quadrilateral is a square, you just need to prove that the diagonals are equal and meet at right angles. For a rectangle, just that the diagonals are equal. For a kite, diagonals have to meet at right angles, and for a parallelogram, the diagonals bisect one another. Let's look at that same question, but this time we're going to use the diagonals to prove it. So we'll form PR and QS. The length of PR is square root of 125, and the length of QS is also the square root of 125. So since the diagonals are equal, PQRS is a rectangle. You also need to know the properties of equilateral, isosceles and right-angled triangles. I'm not going to go through those because I'm sure you know them. But here's one that you might not know. The line from the apex of an isosceles or equilateral triangle is the perpendicular bisector of the opposite side, and that can come in handy. Now there are three specially named lines in a triangle, which is important to be familiar with. The names aren't that important, but the concepts are. So there's an altitude, that's the line from a vertex perpendicular to the opposite side. There's a median, that's the line from the vertex bisecting the opposite side. And there's an angle bisector, and that's the line that goes straight through the center of this angle. You can see that in each case, these lines meet at a certain point. And not surprisingly, in an equilateral triangle, these lines are all the same. Now there are many circle geometry theorems, but these are the three that are most important. So the first one is angle in a semicircle is a right angle. That means from the diameter, any angle you can draw that touches the circumference is going to be a right angle. The second one is the angle between a radius and a tangent at the point of contact is a right angle. And then finally, a radius bisects a chord at right angles. Okay, let's prove that the angle in a semicircle is a right angle. I'm going to start by constructing the vector OB. Now, what we really want to do is find an expression for the vector AB and another one for BC, do the dot product and show that's equal to 0. So let's start with AB. It is equal to AO plus OB. Now the vector BC is the difference between OC and OB, but OC is the same vector as AO. Now let's do the dot product. So AB dot BC is AO plus OB dot AO minus OB. Now this is the difference of two squares, so we're going to get AO dot AO, and remember that is the magnitude of AO all squared, take away OB dot OB. So that's what we end up with. But these two are both radiuses of the same circle, so they have the same length. So that is equal to 0. And so we've proved it. Now let's prove Pythagoras' theorem. Now you've probably heard me say a few million times how much I love vectors because they make life so easy. To prove Pythagoras' theorem without vectors takes pages. In a few seconds you're going to see how easy this is. Consider the right-angled triangle formed by the vectors A, B and C. Now what we'd really want to do is prove that the magnitude of B all squared is equal to the magnitude of C all squared plus the magnitude of A all squared. So let's start with what we want. The magnitude of B all squared must be equal to B dot B. But vector B is the same as vector A plus vector C. Expanding that out, I'm going to get A dot A, which is the magnitude of A all squared, plus 2 times A dot C, plus magnitude of C all squared. But what is this? Because A and C are at right angles, the dot product is 0. Therefore, the magnitude of B all squared is equal to the magnitude of A all squared plus the magnitude of C all squared. And we're done. All right, let's finish off with a past exam question. In the diagram, OA is the vector A, OB is the vector B, C is the midpoint of OA, vector OF is 1/6 of FB. It is also given that AD is equal to lambda times AF and CD is equal to mu times CB, where lambda and mu are both real numbers. Part A, part 1, find the vector OF in terms of B. So OF is here. We know that it is 1/6 of the vector FB. And so finding OF, that must be 1/7 of the whole vector B. Part 2, find the vector AF in terms of A and B. So always start with what we just were asked to prove, which was OF. Okay, so let's form a vector equation for AF. It is going to be OF take away A. But we know that OF is 1/7 of B, and so the vector AF must be 1/7 of B take away A. Part B, part 1, find an expression for the vector OD in terms of A, B and lambda. So OD is here. Again, we're going to start by forming a vector equation. It is A plus AD. And AD is going to allow us to get lambda into the equation. Now AF is here. It is equal to OF take away A. And we figured out OF in the first part, so substitute that in, tidying it up. We have 1 minus lambda times A plus lambda on 7 times B. Part 2, find an expression for OD in terms of A, B and mu. So this time we want to use this part here. But we'll start the same. OD is equal to OC plus CD. And CD is mu times CB. We also know that OC, given that this is the midpoint, is going to be half of A. And CB, which is all the way along here, that is going to be B take away half of A. And tidying it up, we have a half of 1 minus mu times A plus mu B. C, show that mu is equal to 1 on 13 and find the value of lambda. Now in the previous part we found two different expressions for the vector OD and they must be equal to one another. So we can form simultaneous equations by comparing coefficients of the two vectors. So we have this and we have this. Now we want to find mu, so let's eliminate lambda. Substituting that in here and tidying it up, we end up with mu is equal to 1 on 13, and then putting that back into here, lambda must be equal to 7 on 13. D, deduce an expression for the vector CD in terms of A and B only. So we were given that CD is equal to mu CB and mu is equal to 1 on 13. And CB, which is here, is B take away a half A. Finally, given that area of the triangle OAB is equal to K times the area of triangle CAD, find the value of K. So we're going to use the cross product here. So area of this triangle here is going to be a half times the magnitude of A cross B. Similarly, finding this area here, and that's that little tiny triangle in there, it is going to be a half times, this is a half of A, and then CD we found in the previous part. We can tidy this up a little bit and bring this half out and the 13th out. And so we end up with A cross B take away a half A. Now, the distributive law also works with the cross product. So this is the same as A cross B, take away half, A cross A. But the cross product between a vector and itself is 0. So that part is eliminated. And so if we want to know what K is, it's going to be 1 on 26. And that's it for the topic of vectors.